So we've got the Haber process. We've got to talk about equilibrium, which means we've got to talk about the Chatelier's principle. Roll that graphic, let's go to work. Hi, I'm Paul, this is Science That Sticks. Welcome back. In this short episode, I'm going to go through some concepts that you may need to stop, think to yourself, play it again, and then go over it again. So I've already started with this reversible reaction to make ammonia from nitrogen and hydrogen. It's a balanced equation. I've got this little symbol here that shows that it is a reversible reaction. There's a forwards direction and there is a reverse direction. Now, there's a couple of things that can affect the position of equilibrium. The rate of the reaction can also be affected too. It's affected in the same manner that all other chemical reactions are affected. A change in pressure will increase or decrease the rate of the reaction. That's the same as concentration, but because it's a gas, not a liquid, we say pressure. We also happen to have a temperature change. So a temperature change in this reaction can affect the equilibrium, the position of the equilibrium, and therefore the yield. That means the amount of stuff that you get at the end. But it could also affect the rate of the reaction. In this case, it's exothermic in the forwards direction. But that would speed up the reaction. But of course, there's some problems with this. So let's explore the problems and let's explore the Chatelier's principle. The Chatelier's principle states that when a substance is at equilibrium, any change that is applied to the system itself will try to adjust itself so as to lessen the change. In other words, whatever you do to this is going to do the opposite so as to lessen what you have done. Okay? Now that's the basic understanding of it. Now in this case, let's look at this in terms of particles. So we've got nitrogen here, and we've got these three hydrogen molecules here. And I'm just going to colour these in so that we can see that there are you can see the different atoms. So there we go. Now, there is a pressure change. The pressure is greater over here than it is over there. Why is that? Well, that's very easy. We have 1 molecule, 2, 3, 4 molecules of gases as reactants. The product, there's only 2 molecules of gas because remember these atoms are covalently bonded to that atom and so on. So we've got 2 gases here, 2 molecules as opposed to 4 here. So because we've got less gas, that means we have a lower pressure. If we increase the pressure here, we squeeze the volume, the system will adjust itself so as to lessen the change. That means it will produce more product. Easy enough. If you decrease the pressure here, this will have the opposite effect. Now in this case, it's worth thinking about heat as an exchange. If it's exothermic in the forwards direction, we want to be able to keep it cold so that we can move the position of equilibrium and the yield to the right. But there's a problem with that. If you cool a reaction down, you slow a reaction down, you'll have a nice yield, but it will take a long time to get there. We've also got a different problem with this. We need quite a high temperature because we want the yield to be made in good time. We also happen to have a gas, and a fairly high pressure is still required for this. It's several hundred atmospheres, so that's quite a lot of pressure. So why do we need something with such high pressure? Well, the answer for that is to ensure that we get a decent yield in a decent rate. If we have too high a temperature, unfortunately, we end up with safety concerns, okay? Or rather rate concerns, but a high pressure, high temperature, all in a sealed area, where you've got safety concerns, big safety concerns. You've essentially made something that could detonate, and you don't want that. Low pressure, low temperature, that would benefit massively, but your yield would be high, but it would take you such a long time to get there. It would be uneconomical, okay? So that's pretty easy. The other really nice thing about this is the catalyst for this is a solid iron mesh, which means it's heterogeneous to the reactants and the products. In other words, you can always get back the catalyst, which you should be able to anyway. But that's Le Chatelier's principle. I'll do more another time. Until next time, ladies and gentlemen, stay cool. Be prepared for the exams that are coming up this year. Take care. Bye-bye.